Hello. We will now answer the three questions that I described in the last video. The first question was if if it is possible to shadow a variable, here x, with caps, using a constant. Here's the constant. Okay, if I attempt to compile, there's one error here, refutable pattern in local binding. So it pattern matches what we're trying to do with the specific error, which which is um, uh, it pattern matches with this error, which is completely irrelevant with what we are trying to do. It does not match uh, with our goal, where we are trying to shadow a variable using a constant. So here the solution, the help that is provided to us is it. We are lucky that this here, the help also solves our problem, but the error is completely irrelevant to what we are trying to do. We are trying to shadow a variable using a constant. Here, that is not pattern matched by the compiler, and it is our fault, not the compilers, for not doing it. We should have known better. Okay, so the second question was if we can, let me check, if we can create a variable in the global scope. It is also not possible. Here I create variable x in global scope, and inside the main function I attempt to print its value. If I attempt to compile, an error will be generated. Here, in this example, in this question, the compiler correctly pattern matches what we're trying to do. Let cannot be used for global variables. Consider using static or const instead of let. Okay. I'm not implying, just a quick note, that I'm not implying that previously, in the previous example here, the compiler was incorrect. Okay, it is it tries to be as helpful as possible. Okay, there is nothing else. I also there was a third question that I had, whether Rust compiler depends on LLVM. The answer to that is, from a quick Google search, it's yes, that it does depend, which is a good thing. But I didn't dive deeply. Maybe it does not depend anymore, but it used to. The takeaway is that at some point it did depend, and it may still depend on LLVM. Okay. Let's continue with the 3.2 chapter, data types, the available data types. every value in Rust is of a certain data type, which tells Rust what kind of data is being specified so that it knows how to work with that data. We'll work at two data types subsets, scalar and compound. Keep in mind that Rust is a statically typed language, which means that it must know the types of all variables at compile time. The compiler can usually infer what type we want to use based on the value and how we use it. In cases when many types are possible, such as when we converted a string to a numeric type using parse in the comparing the guess to the secret number section in chapter 2, we must add a type annotation like this. Here is the type annotation. In cases when many types are possible, okay, if we don't add the type annotation shown in the preceding code, Rust will display the following error, which means the compiler needs more information from us to know which type we want to use. Okay, so type annotations needed. Here, the guess variable type must be known at this point. Okay. You will see different type annotations for other data types. Okay, so my question for this here is, can't Rust infer, the compiler infer what type we want to use based, for example, if I write let guess equals sorry, if I write here let guess equals 8 and then print line guess is guess, compile, Rust compile, it compiles, no error is being generated here. It compiles and it prints. So here at this point 8 can be signed, unsigned, it can be of 8 bytes, of 4 bytes, 2, 1 byte. The type of guess is not could be, it's not one type. It could be of multiple types. Any of those that I said is valid, but no error is generated. So here this is not exactly correct. I read again. In cases when many types are possible, such as this, we must add a type annotation. So that is incorrect. But never mind. Okay, we can proceed. If we don't add the, yeah, we get the error here. Okay, so let me run this here. Let me copy this and attempt to run. Okay, what's the pattern? The pattern is it's this. Okay, compile. Yeah. Okay, so we do not know what parse does. Cannot satisfy this here. So this reminds me of of templates because less than something inside and greater than. So that's in C++, this pattern here is a template. So maybe it has to do with compile time knowledge of the it needs explicitly the data type. So the template is populated, and then inside of this namespace, the error is the same as underscore. So this here is underscore, and this maybe these two underscores are the same. So the takeaway is that in this context, we do need to specify the variable type of guess of the variable guess. It's mandatory. So we need to learn what's going on here. So this will be a question for one of the upcoming videos that I will upload, possibly here, possibly in later when we talk about templates and yeah. I will note it and answer it then. Okay, we have scalar types. A scalar type represents a single value. Rust has 4 primary scalar types: integers, floating point numbers, booleans, and characters. You may recognize these from other programming languages. Let's jump into how they work in Rust. Okay, so integer types. An integer is a number without a fractional component. We used one integer type in chapter 2, the unsigned of 32 bits type. So it's unsigned 4 bytes. This type declaration indicates that the value it's associated with should be an unsigned integer. Signed integer types stand with I instead of U. That takes up 32 bits of space. Table 3.1 shows the built-in integer types in Rust. We can use any of these variants to declare the type of an integer value. Okay, 8-bit, 16, here's the corresponding for both assigned and assigned. And we also have the architecture dependent size. Similarly, as in C. C does not have a 128-bit integer. That's very, very big number. It can capture very big numbers. Each variant can be either signed or unsigned and has an explicit size. Signed and unsigned refer to whether it's possible for the number to be negative. In other words, whether the number needs to have a sign with it, or whether it will only ever be positive and can therefore be represented without a sign. It's like writing numbers on paper. When the sign matters, a number is shown with a plus sign or minus sign. However, when it's safe to assume the number is positive, it's shown with no sign. Signed numbers are stored in 2 complement representation. So this is what should be, yeah, it's a Wikipedia link. Each signed variant can store numbers from in this range, inclusive, where n is the number of bits the variant uses. So an assigned number of a single byte can store numbers in this range, which equals to minus 128 to 127. Unsigned variants can store numbers from 0 to in this range. So 1 byte can store here 0 to 255. Additionally, the I size and U size types depend on the architecture of the computer your program is running on. 64 bits if you are on a 64-bit machine, and 32 bits if you are on a 32-bit architecture. You can write integer literals in any of the forms shown in Table 3.2. Note that number literals can be multiple numeric types allow a type suffix, such as 57. So this is a literal, number literal. It's 57 in as unsigned integer of 1 byte to designate the type. Number literals can also use underscore as a visual separator to make the number easier to read, such as 1000, which will have the same value if you had specified 1000 without the underscore. So this is some examples of literals. So a decimal here with the underscore, similarly to how we had one in the 1000, a hexadecimal, 0x the prefix, and then this is 1 byte, all ones. An octal, binary, OB for the binary, and then this is F and 0 in hex. It's corresponding to F0. Here the octal has the prefix of 0O, lowercase o. And then for bytes, B and then a character. So A, yeah, I don't remember exactly. So how do you know which type of integer to use? If you are unsure, Rust's defaults are generally good places to start. Integer types default to I32. The primary situation in which you use I size or U size is when indexing some sort of collection. Okay, so integer overflow is next. Oh, sorry. Let's say you have a variable of type U8 that can hold values between 0 and 255. If you try to change the variable to a value outside of that range, such as 256, integer overflow will occur, which can result in one of those of two behaviors. When you're compiling in debug mode, Rust includes checks for integer overflow that cause your program to panic at runtime if this behavior occurs. Rust uses the term panicking when a program exits with an error. We'll discuss panics in more depth in the Unrecoverable Errors with Panic in section chapter 9. When you are compiling in release mode with the -- release flag, Rust does not include those checks for integer overflow that cause the panics. Instead, if overflow occurs, Rust performs 2's complement wrapping. In short, values greater than the maximum value the type can hold wrap around to the minimum of the values the type can hold. In the case of U8, the value 256 maps to 0. The value 257 becomes 1, and so on and so forth. The program will not panic, but the variable will have a value that probably isn't what you're expecting it to have. Relying on integer overflow wrapping behavior is considered an error. To explicitly handle the possibility of overflow, you can use these families of functions provided by this std for primitive numeric types. Wrap in all modes with the wrapping method such as wrapping add. Okay, so those functions, so std library provides a family of functions, these families of methods provided by the std to actually handle the possibility of overflow. Okay, so even if we compile with release flag, or in any case, whether it is release or debug, we can use these here functions to explicitly handle possibility of overflow. In case it is it has to do with the user's input, or it's not the problem of we cannot determine the overflow at compile time. Maybe it's on runtime. If it is on runtime, we need those functions to if we play with numeric stuff, numeric analysis and those algorithms. So wrap in all modes with the wrapping methods. Return the none value if there is overflow with the checked methods. Return the value and a boolean indicating whether there was an overflow with the overflowing methods. Saturate the values minimum or maximum values with the saturating methods. So here this information is not enough. I cannot understand what those methods are doing exactly. I assume that all the overflowing methods return the value and the boolean. But what does it mean to saturate the values minimum or maximum values exactly when using the saturating family? Okay, this is the second question of today. I will note this after I'm done recording. Floating point types. Let's go to the floating. We are still in the scalar family. After integer, we go to floating. Rust also has two primitive types for floating point numbers, which are numbers with decimal points. Rust's floating point types are F32 and F64, which are 32 bits and 64 bits in size respectively. The default type is F64, because on modern CPUs it's roughly the same speed as F32, but is capable of more precision. All floating point types are signed. Here's an example that shows floating point numbers in action. Okay, so inside the main function, we declare two variables, the x and the y. The x is equal to 2, which its type is implicitly declared as F64 because this is the default type of floating point types. Here, the y is F32 because we explicitly said so, but from what I've understood, 3 is F64 temporarily, and F64 data type initializes an F32 data type. Floating point numbers are represented according to the IEEE 754 standard. All right, so numeric operations. Rust supports the basic mathematical operations you would expect for all the number types: addition, subtraction, multiplication, division, and remainder. Integer divisions truncates toward 0 to the nearest integer. The following code shows how you would use each numeric operation in a let statement. So here's the addition, the subtraction. This sum is 11. Here we subtract, 91.2. Add the product, the division, the remainder. Each expression in these statements uses a mathematical operator and evaluates to a single value, which is then bound to a variable. Appendix B contains a list of all operators that Rust provides. The Boolean type. As in most other programming languages, a Boolean type in Rust has two possible values, true and false. Booleans are 1 byte in size. The Boolean type in Rust is specified using bool. For example, here, this is a bool, this is also a bool, but with explicit type annotation. One other question I have is for the floating types here, if I add after the 2 here, and where I have the cursor before the semicolon, if I add F32, will X be of type F32 or F64? This is a question. Okay. The main way to use Boolean values is through conditionals, such as an if expression. We'll cover how if expressions work in Rust in the control flow section. The character type. Rust's char type is the language's most primitive alphabetic type. Here are some examples of declaring char values. Here, C is a character which is holding Z. Z is a character which holds, this is the capitalized Z or the set of numbers. Z. It looks like it, yeah, okay. Yeah, it's not the same. Yeah, it's different. It's the set of the numbers for the integers of the the integers. And then it has also here an emoji. Note that we specify char literals with single quotation marks as opposed to string literals which use double quotation marks. Rust's char type is 4 bytes in size and represent a Unicode scalar value, which means it can represent a lot more than just ASCII. Accented letters, Chinese, Japanese, and Korean letters, characters, emojis, and zero with spaces are all valid char values in Rust. Unicode scalar values range from U plus 4 zeros to U plus D7FF, and the other range here. However, a character isn't really a concept in Unicode. So your human intuition for what the character is may not match up with what the car is in Rust. We'll discuss this topic in detail in storing UTF-8 encoded text with strings in chapter 8. Okay, compound types. Compound types can group multiple values into one type. Rust has two primitive compound types, tuples and arrays. The tuple type. A tuple is a general way of grouping together a number of values with a variety of types into one compound type. Tuples have a fixed length. Once declared, they cannot grow or shrink in size. We create a tuple by writing a comma-separated list of values inside parentheses. Each position in the tuple has a type, and the types of the different values in the tuple don't have to be the same. We've added optional type annotations in this example. Here, a tuple which consists of an integer of 32, f64, and assigned 8. So here, at the first position, we could also add a negative number. Whereas here at the last, we could not do that, use a negative, because it is unsigned. We would get an error. The variable tup binds to the entire tuple because a tuple is considered a single compound element. To get the individual values out of a tuple, we can use a pattern matching to destructure a tuple value like this. A tuple here, and then we destructure it. The value of y is y. This program first creates a tuple and binds it to the variable tup. It then uses a pattern with let to take tup and turn it into three separate variables, x, y, and z. This is called destructuring because it breaks the single tuple into three parts. Finally, the program prints the value of y, which is 6.4. Correctly, because here is the second, which is here second, y, the variable y, which is then printed. So it is indeed 6.4. We can also access a tuple element directly by using a period followed by the index of the value we want to access. For example, here again we have the same tuple as above. 500 is the .0 and then .1, so this is a cool way to fetch the corresponding value. Yeah, cool way. Period and then followed by the index. This program creates the tuple x and then accesses each element of the tuple using their respective indices. As with most programming language, the first index is a tup. In the tuple is 0. The tuple without any values has a special name, unit. This value and its corresponding type are both written as opening and closing parentheses without anything in between, and represent an empty type, an empty value, or an empty return type. Expressions implicitly return the unit type if they don't return any other value. expression implicitly return the unit value if they don't return any other value. All right. Expressions. Okay. The array type. So this is not clear to me what's going on here. We will see. I will also note this and we will come back to it. In C, expressions do return the value that has been assigned. Here, I guess, when does an expression not return anything? Yeah, I will keep that in mind and note it down, and we will revisit. The array type. Another way to have a collection of multiple values is with an array. Unlike a tuple, every element of an array must have the same type. Unlike arrays in other languages, arrays in Rust have a fixed length. We write the values in an array as a comma-separated list inside square brackets. This is like Python. Arrays are useful when you want your data allocated on the stack, the same as the other types we've seen so far, rather than the heap. We'll discuss the stack and the heap more in Chapter 4, or when you want to ensure that you always have a fixed number of elements. An array isn't as flexible as the vector type, though. A vector is a similar collection type provided by the standard library that is allowed to grow or shrink in size because its contents live on the heap. If you are unsure whether to use an array or a vector, chances are you should use a vector. Chapter 8 discusses vectors in more detail. However, arrays are more useful when you know the number of elements will not need to change. For example, if you were using the names of the month in a program, you would probably use an array rather than a vector because you know it will always contain 12 elements. You write an arrays type using square brackets with the type of each element, semicolon, and then the number of elements in the array, like so. Here, the type of each element, then semicolon, and the number of those elements, of such elements. Here, 5 elements of I32 type. Here, I32 is the type of each element. After the semicolon, the number 5 indicates the array contains 5 elements. You can also initialize an array to contain the same value for each element by specifying the initial value followed by a semicolon and then the length of the array in square brackets and shown here. The array named 5 will contain 5 elements that will all be set to the value 3 initially. This is the same as writing A equals 5 3s, but in a more concise way. Array element access. An array is a single chunk of memory of a known fixed size that can be allocated on the stack. You can access elements of an array using indexing, like this. Here we've got our array, and then the first element is at index 0, the second at index 1, so on and so forth. In this example, the variable named first will get the value 1. This is the first value in the array, because that is the value at index 0 in the array. The variable named second will get the value 2 from index 1 in the array. Invalid array element access. Let's see what happens if you try to access an element of an array that is past the end of the array, out of bounds. Say you run this code similar to the guessing game in chapter 2 to get an array index from the user. Here is our array. We request from the user to read from stdin. We get to the variable index as a character. Then we convert the character to number. So here is the number, and attempt to read the item inside the array at index specified. This code compiles successfully. If you run this code using cargo run and enter 0, 1, 2, 3, or 4, the program will print out the corresponding value at the index in the array. If you instead enter a number past the end of the array, such as 10, you'll see output like this. Panic. Index out of bounds, the len is 5, but the index is 10. Note, run with Rust backtrace1 environment variable to display a backtrace. The program will resulted in a runtime error at the point of using an invalid value in the indexing operation. The program exited with an error message and didn't execute the final print line here. Statement. When you attempt to access an element using indexing, Rust will check that the index you've specified is less than the array length. If the index is greater than or equal to the length, Rust will panic. This check has to happen at runtime, especially in this case, because the compiler can't possibly know what value a user will enter when they run the code later. This is an example of Rust's memory safety principles in action. In many low-level languages, this kind of check is not done, and when you provide an incorrect index, invalid memory can be accessed. Rust protects you against this kind of error by immediately exiting instead of allowing the memory access and continuing. Chapter 9 discusses more of Rust's error handling and how you can write readable safe code that neither panics nor allows invalid memory access. Okay, so the question is, can I if we compile with release, does this check still happen? Because this check introduces overhead, and I do not want that to pay that overhead. Maybe if we compile with debug or with just Rust C without any flag, maybe the check will be run. But when we compile with release, the check does not happen. We will have to. So this is the last question I have.